So for this week's video, let's try to come up with some applications for what we did last time, where we minimized quadratics. Take a vector in Rm, and that should have a little vector sign over it, and take a vector subspace of Rm. Now here's a problem. Given that vector in the vector space and that subspace of the vector space, what is the closest point in the subspace to the fixed given vector? The point is that you're going to ask for the norm of v, let's call it v tilde, minus b, where v tilde is the closest point in v to b. So range over all v's in v, find the closest one to b, and find the minimal distance. The point is that that norm is, well, with the norm squared, is a quadratic, and so that's going to let us use our previous techniques. So maybe b itself is not a member of v. So how far away is it? How close is it to living in the vector space? Of course, if that vector b is a member of v, then, well, the closest thing in v to b is b itself. So you see that b minus b is the zero vector. Well, the norm of the zero vector is 0. So the minimal distance is 0. But what happens in the other case? What happens if b is not in v? Well, that's when we're going to go to minimizing distances. So let's come up with a strategy. The general plan that we're going to use will actually work not just with the Euclidean norm in Rn or Rm, but any norm that comes from an inner product. And we defined inner products last time as being bilinear, symmetric, and positive definite. So then the norm squared will be this, well, the norm of a vector squared is just v dot v. There's supposed to be a square there. Okay, so if you look at that long enough, then if you try to compute the norm of v minus b, and that's, we're just going to try to minimize that over all v's, well, you can take the square of that norm, that's v minus b dot v minus b, and using FOIL from, I don't know, middle school, you can get that that's v dot v plus b dot b minus 2 v dot b, and then v dot v is the norm of v squared, and b dot b is norm of b squared. So in order to go any further, let's fix a basis of the vector space v. That's the vector subspace of Rm, and let's say it is n-dimensional. So I can write my vector v, which is an arbitrary member of big V, in this basis, and I'm going to write it as x1 times v1 plus x2, that says x2, plus x2 times v2 plus, and so on, plus xn times vn. Now these x1 through xn are called the coordinates of little v relative to the basis, v1 through vn. So these these coordinates are some numbers, say real numbers. And let me just put them into a vector, x1 through xn, call it a column vector for convenience. So if you use this expression for the vector v, then the norm of v squared is still v dot v, and that's x1 v1 plus x2 v2 plus, and so on, xn vn. That's our expression for v in terms of this basis, dotted with itself, x1 v1 plus dot 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 plus xn vn. Okay, and if you use the bilinearity of the inner product to break that up, you're going to get a combination of vi dot vj's, and exactly which ones are written here. The summation from I and j go from 1 to n of xi xj vi dot vj. So I set k to be this matrix with the kij's, and kij's are exactly the coefficients vi dot vj. Those should have vector signs on them. This is called the Gram matrix of the inner product. So what is the norm of v squared then? It's just x transpose kx. Very similarly, if you take, no, erase that. Thank you. If you take v dot b, we're just decomposing each term in our norm of v minus b squared. So you take v dot b, you get x times the summation of xi's times vi dot b's. And let me take the vector f to be v1b, v2b, down to vnb, again for convenience. So this v dot b thing really just looks like x transpose f. X transpose f. And finally, if you wanted to look at the norm of b squared, well, that's just some number. Let's call it c. And so altogether, your norm of v minus b squared looks just like this form that we saw last time. X transpose kx minus 2, you see where that 2 came in, x transpose f plus c, where c again is just norm of b squared, some fixed constant. So we know how to minimize that. So let's combine all this, let's collate everything that we've got together in one result. If you fix a basis, v1 through vn, of some vector space v, and let's think of v as a subspace of Rm. So v1 through vn are m vectors, and I take n of them, so I have an n-dimensional subspace of vm. And you fix some vector b, that's a member of Rm, and again that b should have a vector sign over it. Then the way to find the closest point in V to B is, well, that point is going to be called V twiddle, V tilde. And in the coordinates, so in terms of this basis, the coordinates, say they're x1, v1 through xn, vn. That member of V, which is the closest vector to B, is determined uniquely by the following equation. And this equation should look very familiar because it should be exactly the same as the equation that we used to minimize distance. The equation is just kx equals f, where what is f? F is just A transpose B. And if you want to know that distance, you just take the norm, so the distance between B and this vector V tilde, which is the same as the distance between V and the whole vector space V, is just the norm of V tilde minus B. So an algorithm to let you do this in practice is as follows. Take A to be the matrix with V1 as the first column, V2 as the second column, and at the end Vn as the nth column. These are M vectors. Let me fix that. That's the A that we're talking about. Stick the basis as the columns of a matrix. That's an M by N matrix. Now define K to be A transpose A, the Gram matrix. This has to be symmetric. It has to be square, n by n. Set F to be A transpose B, and set C to be the norm of B squared. Then, what are you looking at? If you take V to be x1 v1 plus x2 v2 plus xn vn, then the norm of v minus b squared, well, v is a times x, isn't it? So this is ax minus b squared, and that's ax minus b times, oh, there should be a transpose there. Ax minus b transpose times ax minus b, which, if you follow that through, is exactly the form that we wanted. X transpose kx minus 2x transpose f, x transpose, thank you, f plus c, where c is that number norm b squared. And we already know exactly how to minimize that. which we know how to minimize. All we have to do is solve the equation kx equals f. So that means that and it's unique, the unique minimizer, the unique closest point in V to B, is exactly V tilde, which is just K inverse times F. K inverse times F. Okay, so let's do a concrete example. Suppose I take V to be the span of the two vectors 1, 1, 0 and 0, 0, 1. In R3, those are three vectors, and there are two of them, so I have a two-dimensional subspace of R3, that's called the plane. You can tell that those two vectors are linearly independent pretty easily. So what plane is this? Well, that's the plane with the equation y equals x, right? The first coordinate has to equal the second coordinate, and the third coordinate is free. So you're looking at the plane with the equation x minus y equals 0. Take the following vector, fixed vector in R3, 0, 2, 3. Not a member of this vector space, because the x-coordinate is 0 and the y-coordinate is 2, and those aren't the same. But still, you might ask yourself, well, how far away from that vector space, from that plane, is this vector b? What's the distance between b and v? That's an entirely reasonable question, and we're going to talk soon about projections, which is a different way of thinking about this. But for now, we'll use our minimization techniques. So the algorithm says first, let A be the matrix whose columns are given by your basis. So that's 1, 1, 0, 0, 0, 1. Then compute A transpose A, that's K, and when you do that, you're going to get this diagonal matrix 2, 0, 0, 1, which is a very nice matrix. And when you compute F, that's A transpose B, you're going to end up with 2, 3. Pause the video and make sure you do that. Actually compute those things. Then C is the norm of 0, 2, 3 squared. That was B. B is 0, 2, 3, and F is 2, 3. So when you take that norm squared, you get 13, because square root of 13. No, I'm taking the norm squared. So 2 plus 9 is 4 plus 9 is 13. Good. So the closest point is going to have coordinates x1 and x2. So V looks like x1 times 1, 1, 0 plus x2 times 0, 0, 1. And x1 and x2 are going to be determined uniquely because K is a positive definite matrix. It's non-singular, so the solution to this system of linear equations that I'm writing down is unique. K times x1, x2 should be F, which at the end of the day means I'm going to row reduce the matrix again. The matrix goes 2, 0, 0, 1, x1, x2 equals 2, 3, and I don't have to do much row reduction because it's already diagonal. Diagonal matrices are your friend. So what do you get? You get x to be the vector 1, 3. x1 has to be 1, and x2 has to be 3. So that means that your vector v, which is the closest point in V to B, is 1 times 1, 1, 0 plus 3 times 0, 0, 1, or 1, 1, 3. And you can see that's clearly a member of the vector space. How far away were you? This approximate, to this approximation of B? Well, you just take the norm of 1, 1, 3, that's the V tilde, it should be V tilde, minus B, 0, 2, 3, and that's just the norm of 1 minus 1, 0, which is the square root of 2. So this vector, 0, 2, 3, is the square root of 2 units away from B. Now let me rephrase this. Let's talk about this a different way. 0, 2, 3 is not a member of the range or column space, whichever phrase you want to use. It's not in the range of the matrix A, 1, 1, 0, 0, 0, 1. Because the range of that matrix A is exactly the column space, and the column space is the vector space we wanted, the plane. So 0, 2, 3 is not in that column space, which exactly means that 1, 1, 0, 0, 0, 1, A times xy equals 0, 2, 3 has no solution. This is an inconsistent system of linear equations. There's no solution at all. There is no exact solution. But you might still want to solve a system like that, or find the nearest thing to a solution of a system like that. And so the best approximation, in the sense of the least squares, so the least squared distance of the vector. Approximate solution is exactly given by xy equals, let me give myself a second. Approximate solution is x equals 1, 3. That was the vector we found, the coordinates. And you find that multiplying this matrix times this vector, a times 1, 3, and you get, if you multiply that out, 1, 1, 0 times 0, 0, 1, or 1, 1, 0, 0, 0, 1 times 1, 3, gives you 1, 1, 3. That guy is your nearest member of the column space. And it's only root 2 units away from 0, 2, 3. That root 2 is called, in official lingo, is called the least squares error in this least squares solution. So this 1, 3 is called the least squares solution, and the distance away from the vector space, from the column space of A, is called the least squares error. Let's do another example. Maybe this will give us some practice with some old techniques too. So take the following subspace of R4. Take the set of all vectors v1, v2, v3, v4 that satisfy the following. v1 plus v2 plus v3 plus v4 is 0. So the sum of the coordinates of this vector are supposed to be 0. Coordinates add up to 0. So you can prove, without much difficulty, I hope, that this is a vector subspace of R4. If you can't prove that, we need to talk. But you should be able to prove that without much difficulty. And so you can rewrite this if you want. You can think about it as the set of vectors v1, v2, v3, v4, so that when I multiply them by the matrix that I've written here, 1s in the first row and 0s elsewhere, I get the 0 vector, because the first entry should be v1 plus v2 plus v3 plus v4, and that's 0, and then the rest of the columns give you no new information. So I've added one linear condition to my set of vectors, and that should knock the dimension down by 1. This is the null space of that matrix, and I hope that you're very good at computing null spaces now. It turns out that you can, so you see that the last 3 variables are free, and the first variable looks like minus the second, minus the third, minus the fourth. Let me just put the minus signs on the other side. So I have, this looks like the set of all vectors, v2 plus v3 plus v4, minus v2, minus v3, minus v4, where v2, 3, and 4 are free. There can be any numbers you want. So that is a 3-dimensional subspace, because you're making 3 free independent choices. And if you write that out, you get a span of, in v2 you get 1 and a minus 1 and then zeros. In v3 you get 1, 0, minus 1, 0, and in v4 you get 1, 0, 0, minus 1. So those 3 vectors are clearly linearly independent and span this space, because I just checked that it was null space. So that's a basis for the vector space V. So here's a question. How far is it from 1, 1, 1, 1 to V? Clearly 1, 1, 1, 1 is not a member of V, because the coordinates don't add up to 0. So in order to find out how far away it is, let A be the matrix whose columns are given by your basis of V. That's what I've written here. And then A transpose A is easy to calculate. Let me do it slowly. So it's got 2's down the diagonal and 1's elsewhere. Again, you should make sure that you stop the video and compute that yourself. And then F is A transpose B, and B, what do I have 3 1's? There should be 4 1's there. So let's write all that out again. So K is this matrix. F is A transpose times, that's a typo, 1, 1, 1, 1. And I do the computation correctly here, and I get 0, 0, 0. Well, so the coordinates in the basis that I chose for V, and those are just the columns of A, which are the rows of A transpose, so those basis vectors are right there. The coordinates of the closest point in V to B, B being 1, 1, 1, 1, are x1, x2, and x3, meaning V, the closest thing looks like x1, v1 plus x2, v2 plus x3, v3, where x is given by kx equals f. And that just means that you're solving the system of linear equations k times x equals f. Oh, but f is the 0 vector. And K is a Gram matrix. It looked like A transpose A, where the columns of A were linearly independent. So this is a non-singular matrix. It's a Gram matrix. It's positive definite, not just non-singular. That means that the only solution is the trivial solution. So x1, x2, and x3 have to be 0. And that means that the closest point to 1, 1, 1, 1 in V looks like 0 times the first basis vector, 1, minus 1, 0, 0, plus 0 times the second vector, 1, 0, minus 1, 0, plus 0 times the third vector, 1, 0, 0, minus 1. And everybody knows that that's the 0 vector in R4, which is certainly a member of V, but we were a little surprised not to see anything but the 0 vector, not to see non-zero numbers. But in short, what's going on? Well, the distance from the vector space V to the point 1, 1, 1, 1 is just the norm of 1, 1, 1, 1 minus the 0 vector, which is a silly thing to write down. It's just the norm of 1, 1, 1, 1, and that's the square root of 4. That's 2. So why did this happen? How did this get so nice? Normally, we're used to seeing that the closest point in V is some strange combination of the basis vectors. And this time we had non-singular matrix for K. Well, so if K was non-singular and we got only the trivial solution, that was because F was the 0 vector. Okay, how come F was the 0 vector? Well, F is the 0 vector because I got it by taking A transpose times 1, 1, 1, 1, and that means I multiplied, for each coordinate of F, I got the row, each coordinate of F was a row of A transpose times 1, 1, 1, 1 times B. So if B was orthogonal to each row of A transpose, which is really just a column of A, which is really just a basis vector in V, if B is orthogonal to all of those, then B is orthogonal to the whole space. And so there's no way to project B onto V besides, the projection of that is 0. So B is orthogonal to the basis we chose for V. So let's finish this video with one more application. Suppose I give you these 3 points, 0, 1, 1, 2, and 2, 0, 3 points in the plane. And I ask you to find a line, y equals, let's call it mx plus d, so that we don't have confusion with the b that we have in the other slides. Find a line that passes through all 3 of those points. Well, if you plot those points 0, 1, 1, 2, and 2, 0, there's no line that passes through those 3 points. They're not lying in the same line. But you can still ask, what's the line that's closest to passing through them, in the sense of least squares, in the sense that the sum of the squares of the distances from those points to the line should be the smallest possible. So what is the closest approximate line? What is the least squares approximation to a line that passes through those 3 points? Well, let's set up some algebra. If you just plug in those points into y equals mx plus d, it's a d, not a b, then you plug in 0, and you're supposed to get 1. You plug in 1, and you're supposed to get 2. You plug in 2, and you're supposed to get 0. So that's a system of linear equations, 3 equations and 2 unknowns. You can write it as a matrix. 0, 1, 1, 1, 2, 0, and that's times md is supposed to equal 1, 2, 0. And seeing that these 3 points don't lie in a line is exactly the same as seeing that this system of linear equations is inconsistent. There is no line that passes through all 3 points. There's no md that solves this. Still, we want an approximation. We want an md that will get us as close as possible. So, call this matrix 0, 1, 2, 1, 1, 0, call it A, and take K to be A transpose A. And when you multiply those 2 things together, you'll find you get 5, 3, 3, 3. And take F to be A transpose B, where B is this 1, 2, 0. B. All right. So then the minimizer will be m tilde d tilde, call it x. Okay, so when you multiply A transpose B, you get 2, 3. And again, that should be something easy for you to compute yourself. So we're going to try to solve kx equals f. To do that, you're really, again, just using Gaussian elimination. You just adjoin this column 2, 3 to the matrix K, and row reduce it, and you're going to find that x1 is minus a half, and x2 is 3 halves. That means that your m tilde d tilde, which will get you to the closest point to the column space of A, the closest point in the column space of A to B, is minus a half, 3 halves, which is all you really cared about. You don't actually need to know what the closest point to B is in that space in R3. You only care what the line was, and that's exactly given to you by m tilde and d tilde. So your closest line is minus a half x plus 3 halves, and let me draw that. This is what Microsoft Excel is doing when it does linear regression, when it does a line of best fit into the scatter plot of data. This is what it is doing. It is multiplying matrices out and doing this exact procedure as efficiently as it can. So if I plot these 3 points, then I'm going to try to graph minus a half x plus 3 halves. Okay, so plus 3 halves, that gives me my y-intercept halfway in between 1 and 2, and then I go down 1 and, no, down a half and over 1, down a half and over 1, and I draw lines for those 3 points. So my guess was about right. This was going to be approximately the right line that I drew in red at the beginning, but now I have an equation of that line. And so if I thought there was a trend in this data, I could project into the future and see what else. I could make predictions. So these 3 red lines that I've drawn, those are the distances from the data points to the line. And so what I'm doing, this line that I've chosen, is the line that minimizes the sum of squares of lengths of those red lines.